Good morning everyone. We have come to the tutorial session of our course, and I have prepared a tutorial and asked it to be emailed to all the participants, and hope that you have received. If you have not received, please contact the course coordinator. They will send the 2 documents to you. They are 2 PDF files. First one is what you can see in the screen, mini hydro power plant design and integration with DC microgrid, tutorial 1, and our day, and it has 2 pages, and then there is another page containing a map, a portion of a map. And so, these are the 2 documents that must have been emailed to you. So, please download them, and I want you to work on it. So, the tutorial says figure T1 shows a contour map to scale of 1 to 50,000 for a hydropower potential area. Contour heights are given in meters. Suppose no other hydropower schemes have been implemented this area, and you are entrusted to develop a suitable hydropower scheme with a head between 100 meter to 250 meter in any river section shown in the map. Mark the location of the weir, that is diversion point, canal path, forebay tank, penstock and the powerhouse for the selected project on the map. Estimate the gross head of the project, that is the part A. Right. So, I want you to on the this figure using this drawing tool, you can freehand draw, mark these points in the map, right, right, and you must not select. I will just enlarge it a little, and you can refer to the video where we discuss contour maps. If you cannot remember, please refer to the video where we, I hope that it is accessible to them, video is accessible to them. So, refer to that section where we discuss about contour maps and this section, and then you try to do it. And in selecting, now this is a good river, right, this is a good river, but do not select this hairline like small rivers, streams, they are very small, their catchment area will be very small. So, do not select such rivers for your project, right. Select something like this main river, and where you have opportunity for potential power projects, right. So, and then it says further in section B, of the tutorial it says the table overleaf shows the average flow regime in cubic meters per second for a small hydropower project in the area shown in contour map in figure T1. So, that is the page 2. Here you can see daily average flows that we discussed, which have been prepared by a hydrologist, right. So, October 1st flow is this much and so on, right. So, it is given for all 365 days, and then further the tutorial says section B 1, assuming the given flow data table is applicable to the diversion point of your plant. Now, you have marked a diversion weir in your section A. So, assuming that this table is applicable to the river flows that are coming into this point, right, this at the diversion point is applicable to the diversion point of your plant selected in section A above. Prepare the flow duration curve for the location. So, you can again refer to the video where we discussed how the flow duration curve to be prepared. Select flow corresponding to 12% exceedance. Exceedance means the horizontal axis 12% in the flow duration curve as the rated flow. Determine the type of turbine and its capacity. I think you remember that we referred to turbine selection chart. So, you can refer to a turbine selection chart if the video is not clear, you can search in the internet small hydro or mini hydro turbine selection charts. So, similar charts will come up then in the images gallery. So, you can refer to one of them and select a suitable type of turbine for your head and your flow rate, your rated flow rate, which you derive from the flow duration curve you have created. Determine the type of turbine and its capacity. Assume single turbine power plant. So, we assume we are going to have one single turbine. Estimate the annual electricity generation in kilowatt hours or megawatt hours or gigawatt hours. That part we discuss in another discussion. So, you can refer to that section of the video and do it. So, I plan to allow you the first hour, that is 9:30 to 10:30, in fact until about 11 o'clock. So, I will start the next explain the tutorial at 11 o'clock, right, and help you. If you wish, you can even share, I hope that it is possible, you can even share your screen and ask me any questions. So, show me your workout if you wish, right. You can share your map where you have marked the things, and if you have doubts and or any clearance, you can ask after sharing. But I will not be able to do with everybody, but maybe with at least few people I can do it, and then if necessary I will work out it. I will work out the flow duration curve part and the energy generation part depending upon our time availability, and help you, because finally you should be able to do these things yourself. Otherwise, just watching the video and doing it will not do, right. So, try to do it yourself and have your questions and queries lined up, and during the discussion session which we will start at 11 o'clock, we can go ahead with the further discussion. For the time being, if you have any questions now, you can ask. If you have not received your documents, you can also tell. Otherwise, I will stop here and allow you time to do the tutorial yourself, and then come at 11 o'clock to discuss it and further clarify. Any questions you can raise? Hope everybody you have received the documents. Yes, sir, we have shared the document. Okay, good. So, they have shared the document. So, please download into your computer and follow the instructions given in the tutorial page, and then look at the data table, that is flow data table given on the overleaf, and look at the map, and then try to do it yourself. That is the final intention of participating in this course. You should be able to do these things yourself. Okay, then I will stop there. Thank you. Okay, we see you at 11 o'clock. Yeah. Okay. So, we will I hope that you have tried the tutorial, and if you have any verbal questions I can answer, otherwise I will try to do an example project through the given question and try to help you to follow. If you have any verbal questions, you can ask now, online participants. Otherwise, I will go on explaining the the solution. Okay. So, the first part of the question is to mark the location of a weir, canal path, 4-bay tank, penstock and the powerhouse for the selected project on the map. So, here is the map. I will make it a little larger. Okay. So, obviously, there are many opportunities here, large project opportunities also. So, we will go for this main river here. Here is the main river, here, and there are, you can see various contour heights are marked. So, there are many opportunities, but we can use any of them, right. So, let me take the marking tool. So, we can see that there are many contours we can use, but here it is up to the choice is up to the selector who is going to design it. So, I will so we are asked to have about 100 to 200 kind of head. So, we can see between any of these brown dark lines it is 100 meters head difference. So, we can select accordingly and select a suitable place. And also there are choices that you can go in the right bank or in the left bank. So, how do you say left bank and right bank? When you stand somewhere and look at the flowing water, that is downstream, then your right bank is this one, left bank, that is the convention, left bank is the other one. So, this is the left bank, therefore, this is the right bank, right. So, we can go either way, but the choice is we normally look at obstacles, if there are people settled and houses built or any agricultural projects. So, we will try to avoid interference as much as possible and then decide whether to go on the left bank or the right bank, right. So, let us see that so we decided to divert water here at this point, that will be the diversion weir. Right, and then you can go on this contour line. That will be your canal path and come to a suitable close location to the river. Let us say we came here. There are other options also, and then decide to have the penstock here, right, penstock here, and the powerhouse somewhere here. I can't properly write because of this.
Sir, just wait a minute. Because the pen just lift.
Okay, the operator is asking for some time. Let us see. Please wait, our technical support is coming. Okay. So, so we can now change the colors. You can see we came along this line, and here we have the 4-bay tank. I write FB as 4-bay tank, and then the penstock here. This will be our penstock. Again, I can't write. Okay, anyway, you can see, right, penstock here and the powerhouse here. So, that is a typical project. So, then we can count the number of contours we are cutting, right. So, here we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 like, that is between any two lines it is 20 meters. So, 20 into 10. So, our head will be, gross head will be 200 meters, 200 meters, right. So, these are the first part questions. So, you can see now the idea is after doing this course you should be able to identify a location and the project components and see whether they are plausible, that is if they have a say a housing scheme you can't do it, if there are water schemes then you have to look at, then your catchment you can see in the upstream. I will not try to confuse you with marking catchment because you have to do a lot of work and understand, but for the time being be satisfied with this. If you can do these things then it is better. So, we could have come on the left bank also here like this and somewhere here and gone down, that is also a possibility, that is also a possibility, but choice depends upon availability of roads, availability of land, easiness of transportation, right. So, depending upon those things we will select which bank to construct our canal, penstock and powerhouse, right, canal, penstock and powerhouse. I hope this part is clear to you. Any questions on this? Anybody who cannot do it? Okay. So, going to the second part, you can see part B. Assuming the given flow data table is applicable to the diversion point of your plant, prepare the flow duration curve for the location. So, for that they are given a data set. So, the best thing is to copy this entire thing data set onto Excel sheet. Okay. So, I will paste this somewhere here. Okay. I think it pasted in the wrong way. Hmm? Okay. Earlier I could paste it. Yeah, I think it won't work. We will have to convert it. Yes. I don't know whether this PDF version allows that. No, I don't think that this version has the right to, isn't it?
We have converted it online.
Online. Okay, can you email it to me? Yeah, wait. Everybody wait till I got it converted to this thing, because this version doesn't allow and I have to go online and do it otherwise. So, one of the participants will send me the Excel, so you have to get this into Excel. Yeah, give me a piece of paper or something. I am getting this step to other participant. I am getting this into a. Oh, you send it to Umesh. no, send it to Umesh and he will upload it here. Not my one, ask him to send the file to Umesh, and then he can upload it here, Excel file.
Give the mail ID of Umesh.
Is his mail ID.
ଆମେ ଦେଇଦେଇଛୁ ଖାଲି ଆମ ଦେବାର ଅଛି।
सर आपको
Other participant, wait till I get this converted to, maybe you will have the same problem, you will have to convert.
please leave.
Hmm?
Sir, please leave. Just
Okay,
just 1 minute.
okay. The participant, you will also have to convert it to Excel if you, when we want to use it as Excel file. In some Excel versions you could have pasted it and then columns will come right in the right way, otherwise it will go as a picture. Therefore, in that case you will have to convert the PDF file to that page to Excel to work on the numbers. You emailed or? He is doing it. Okay, now we have got the Excel sheet converted to the PDF sheet converted to Excel. We can see the data points here. So, we can see October, November, December, January up to September here. Each day, day 1 to day 31st, flow rate on October 1st 3.354, October 2nd 2.5, June 3rd 0.607 and so on, right, and so on. So, So, now we have to work on it and then see what are the, let us see what are the questions that were there raised in the tutorial, right. Assuming the given flow data is prepare the flow duration curve for the location. Now, we have to study this data set, right, study this data set. So, we can see. So, one of the better ways of studying and seeing what is the range of values that we have here, and what are the ranges. So, let us see what is the maximum value here. So, I will give the entire data range and see what is the maximum value in this data set. It is good to know, then you can, when you categorize them, that is easier then, right. Okay, the maximum value is 9 point is the maximum value, right, is 9.335. Let us see what the minimum value. So, the minimum value is 0.602. So, I think so we have to deal with data points between these two, right, these two values. So, up to 9.355, let us say up to 10, right. So, let us now the smallest value is 0.6. So, let us make class intervals in the range of, say, in steps of 0.5 up to 10. So, we will open a new sheet, let me okay. So, I will write the class intervals like previously, right. So, 0, next is 0 plus 0.5, right. Oh, I typed in the wrong way. I selected the step by 0.5. I think my numbers are small. How can I zoom this? Umesh, can you zoom it a little bit so that participants can see it clearly? View, okay, here. Okay, right. So, I selected, you can select any point, does not matter. So, 0 class interval I have selected as 0.5, right. So, I will copy and go up to about 10. One more. Okay. So, this 0 means, this 0.5 means really 0.02, 0.05, right, that is the class interval, but I have just typed it as 0.5, right. This is really 0.5 to 1.0. So, we must count the data points in this range and put the number here, frequency here, frequency of occurrence, right, here. So, from this table, for example, 0.5 to So, we can see there are many points, 0.6 comes there, 0.5 to 1. There are many data points. So, we can't manually do it. That is why we are going to use the frequency command. Therefore, we can ask the frequency command to count and put into these class intervals, right, put into these class intervals. How do you do that? You select this cells that you want the counted numbers to appear, and we will put a one cage more, one data point more, because in case there are larger numbers than 10, all of them will be counted and inserted into this additional cell, right, inserted into the additional cell. So, I selected this, and now I start typing the frequency command plus frequency open brackets. Then it gives the hint here, data array, bins array, right. Data array is our data table. So, I will give the entire data table, not the date numbers, but the data points here, right, comma, and then the class interval array. Class interval array is this one, not the column A, right. Then there will be a syntax error. So, I will give this column. Close brackets, right. Then you have to type those three keys, control shift enter, that is the frequency commands executing command, right, control shift and enter. Now, you can see all the counted numbers are inserted into the selected cells. This last number is 0 because our maximum data point was 9.3 something. So, there were no point above 10, therefore, it is there is nothing to be put here, but if there were any, could have been here, right. So, there are large number of data points between 0.5 to 1, right, and then this is really 1.0 to 1.5, right. There are 40 points, 40 data points during the year, right, during the year. So, now we can convert this to a flow duration curve by the technique I told you earlier, right. So, we can get the probability. So, altogether there are 365 data points. So, we can count it, the total is 365 data points. So, probability of each day's flow is really the frequency divided by 365. Right, I will put it to, I will adjust the decimal points to 3. So, this is the probability. Then we can calculate 1 minus p to get the inverse shape. You can do parallelly, right, you can do parallel with me. And then to get the percentage, you can multiply by 100. I do not do it in one step, because then that will be confusing to some of the attendants. Then I will adjust the decimal point say to 1. Sorry, I made a mistake there. Here I made a mistake there, because we have to get a cumulative frequency first, right. So, I will insert a column here. And then calculate the probability. We have to first calculate the cumulative frequency. And then calculate the probability. So, I made a mistake there. Okay. And now calculate 1 minus p. E5. Okay. Now the rest is correct. Now we have the Q, flow rate, and the exceedance or the percentage time that flow rate is available, right. So, we can now draw a graph between this column and this column, right, a graph between these two columns, which will be your flow duration curve. So, let us do it and see. I will select I am a bit unfamiliar with this version of Excel. I selected the maybe my selected chart type was not correct. Let us see this one, it will work. Select data, add x values will be your exceedance. And y values will be the flow rates. Flow rate. Here, now you get the flow duration curve. You can give a title, etc. Oh, did I do something wrong? I think I did some mistake. Y values, flow data. Okay. 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 Now you can see you get the flow duration curve. You can do it nicely in a better shape, better I think the line is too thick and all that, but this is how you get the flow duration curve, right, flow duration curve, and then you can get the charts, grid and all these things, then you can easily get the numbers, etc. right. Anyway, I will not waste time on that. You can see, right. So, this will be your flow duration curve, right, flow duration curve. Now, you are asked to get let us go back to our, I hope any questions up to this, right, any questions up to this from the online or the physical attendance here, right. So, here you can see now for given flow how many percentage of the days, right. For example, I think we should get this the grid lines and all that, format this, so that you can anyway, anybody having problems in getting the flow duration curve? any online participants, you should be able to do it. And then let us go to, once you go there, you can get the flow corresponding 12% exceedance as the rated flow. So, you can go to your this thing, developed curve and mark 12%, find out where the 12% and get the corresponding flow rate. Let us see it is, you can get the exact value, right, but let us assume that this is 9.8. 14. So, it is somewhere around, I will guess around 1.8. You can get the exact value by enlarging this and having the grid lines. So, it is about 1.8 cubic meters per second, right. You can get the exact value and tell me if you want. It is about 1.8 cubic meters per second, right. So, you can get the exact value. Determine the type of turbine and its capacity. Assume single turbine power plant. So, you can see now your head is, we found 200 meters, right. In my particular case, we found that it is 200 meters approximately. Head is 200 meters and the flow is 1.8 cubic meters per second. Now, you can go to a turbine selection chart. I can refer to my notes, or you can otherwise try the net. Let us try the net. Let us search and see. Here you get many kinds of turbine selection charts here. For example, this one, right. So, most of them are the same. So, they will give the same similar advice, different suppliers will have. So, this is having a lot more details, many turbine types are here. Earlier we restricted our discussion to Kaplan, cross flow, Francis and Pelton and Turbo turbines only. But here they are talking about many other versions that are available, right. There are various other versions. So, we can go use that too. We can go to a simpler one if you want. Now, you can see, now you can mark your flow rate 1, 1.2, sorry 2 is here. So, 1.8 is somewhere here, I think. Oh. Here, right. This is 2. So, 1.8 is somewhere here, you can mark 1.8 and the head is 200. So, 200 is somewhere here, right. So, you are almost close to Pelton. So, you can go for a Pelton turbine, that Pelton turbine. So, the some of these charts will have some limitations, because they are made for small hydros. So, if you go outside, then you have to go for some other chart and see, right. So, you can go for a Pelton turbine in this case, you are almost close to there, right, or else you do not have multiple options as per this chart. You can see some other chart and see whether and also we have to be careful that you refer to an accurate chart, right. So, better to go for to a good manufacturer site and obtain a similar chart, right. There are good turbine manufacturers. For example, there are German here for example. So, we once bought equipment from this supplier. He is a good supplier. So, he will have a lot of information in his these various sheets. So, there are many such equipment manufacturers you can refer to. You can search for small hydropower turbine manufacturers, and among other things they will have somewhere in their documentation turbine selection charts. I do not know exactly what is the place. Let us go to turbines and see. Here you can see this is a good turbine selection chart. So, all the manufacturers will have similar charts, right. Here you can see. Now, our flow was 1.8 and 200 here, somewhere here, right. So, you can here as per this you can go for Turgo, Francis or Pelton, or multiple types are possible. So, this is a dependable one because this is given by a manufacturer through his own experiment, but in some other graphs you are getting in the internet may not be that accurate. That is why I came here rather than using the one that we looked at, because their source we do not know, but a good reliable manufacturer will give a good turbine selection chart. Now, here he says large turbines on request. So, having large flows, right, and bigger heads, your size will be much bigger, right, and smaller turbines also on request. So, this is generally what are used in above 100 kilowatt, you can see above 100 kilowatt and below 35 megawatt, that is the range he is just given us, right. So, our power project is 1.8 200 somewhere here, right, somewhere here, which I can plot here. I can't draw because this is an internet page, okay, right. So, this is how you do select machines, right, design a project, right.
आपका मेल आईडी क्या है?
Anybody want to say something?
It's
It's a question. No, you are discussing. Please mute yourself if you are already in the discussion. Then we are asked to estimate the annual electricity generation, right. We have done the determine the type of turbine and capacity. Capacity now you can calculate. Right, you can calculate using P equals efficiency into Q rho G H. So, capacity we calculate for maximum efficiency, assume maximum efficiency as 90%, right, for the turbine, and the other equipment suitably, generator about 96%. Let me write here. So, we are asked to calculate our head is 200 meters, flow is 1.8, you can get the exact value, I just estimate like that, cubic meters per second, right. And then our equation is efficiency into Q rho G H, efficiency we have to get, right. So, the efficiency will be efficiency of the turbine efficiency of the generator, efficiency of the transformer. Let us stop there, otherwise you can put the transmission line, etc. This is gross head 200. So, net head we can say net head is about, we will allow about 3% loss in the penstock. So, it is about so we will deduct about 3%, net head is about 194 meters. So, turbine efficiency we will take say maximum efficiency is 0.9, generator 0.96, transformer 0.98, right. Someone can simplify these things and tell me how much is this 0.9 into 96 into 98. Then efficiency Q is 1.8. Okay, we will have to, we assume that we have already deducted the environmental flow. Rho is 1000 10 to the power 3, G is 9.81 into H is 194. What is this efficiency value? 84. This say someone says 0.84, and then the plant capacity by multiplying this all the things. You can forget about this, this is in watts. So, you can make it kilowatt by removing this 10 to the power 3. So, it will be kilowatt then. How many kilowatts of our plant's capacity? Two 2900. So, our plant as per this calculation has a capacity of 2900 kilowatt, 2.9 megawatt for the location that we have selected, right. So, depending upon this point you have selected, it will be different, your head will be different, etc., right. But we have assumed the data table applied to you, but in reality you have to get the real data table worked out by a hydrologist, right, hydrologist. Now, it further asks, estimate the annual electricity generation. Then we have to expand this, I will relocate this to elsewhere. Here now we can up to here we use for flow duration curve derivation. Now we can go for our power calculation, right. So, let us assume some values, right. Let us assume this generator and transformer efficiency to be 0.96 into 0.98, how much? Can you work out? 0.96 into 0.98, that is the transformer efficiency into generator. We will assume that to be constant, but the turbine efficiency we can't. Efficiency generator plus transformer. How much? How much is it? 0.98 into 0.96. 0.94. 0.94. We will keep it because we might need that, right. And so, and the Q. Now I want to introduce something new here for you. Last time I did not complicate it for you. Now, we see here, right, I took Q as 0.5, right, 0.5, and let us take a minimum flow, Q minimum, that is the environmental flow. Let us say environmental department said it to be 0.3 or 2, whatever, right. Okay. And now, now here, now in the previous discussion I asked you to take 0.5 as the Q and deduct 0.3 from the, can everybody listen? Everybody, right. Here in the last calculation we took here the available Q as Q available for power generation, right. We took it as q minus 0.03, right, q minus environmental flow. Can you remember q minus? But here now we can make it more accurate by looking at this. This data point, say 271 data points, I will put a color here, right. This 271 data points are points between 0.5 and 1, right. It is not always 1, it is the data points can be in between that, right. So, rather than assuming flow to be 1 for 271 days, we can say it is the average of these two, that is better way, right. Average of these two is the flow available on these 271 days. So, I can make my calculation more accurate if I write here flow minus environmental flow, right. I can write it like this, plus open bracket, right, 0.5 is the previous data point for previous q value plus present value open divided by 2, then minus environmental flow, right. So, this will be more representative rather than saying 1 minus 0.03, then we assume always 271 days to have flow equal to 1, which is introducing an error which can introduce. So, this is a better estimation. So, we will go on doing this. Okay, right, q available. Now, we have selected 0.8 as the 0.8 for the 1.8 as our rated flow. Therefore, we can lock it there. From this point onward, we can say for available for power generation is 1.8, because we can't generate more than that, right. We can generate more than that. So, I will after 1.72 I will lock it to 1.8. Because even though the river has water, we can't use our machines, all the components are sized to, right, all are sized to handle water rate of 1.8 cubic meters per second, right. Now, I have to get, right, we have to get efficiency of the turbine here, efficiency of the turbine here, right. So, therefore, that we will have to again rely upon a efficiency curve of Pelton turbine. So, we have selected Pelton turbine. So, we can refer to a Pelton turbine. Let us see such a graph is available with in the net. I went to can see that there are some graphs here. So, you can get from a reputed manufacturer. I will take a typical one and use, but you can see you can this is the flow rate as proportion of design flow, but this is a percentage flow, right, this is a percentage flow, and for the Pelton it has, as we all know, quite flat, right. So, this is given as a percentage. So, we have to know our percentage flows here, right, percentage flows here, that is out of 1.8, what is the percentage here, right. So, we will have to, we will insert a column again here. Divided by 1.8. Okay. So, you can now approximately get from that curve, right, corresponding to various points that we are into 0.1 to 0.4 etc. Of course, you must do it in accurate way, right, 0.1 to 0.4. So, let us say 0.4, you can see the Pelton has already by 0.4, it is already 90 level. So, you can see it is no problem assuming all the values as 90 for our case, right, already it is in 90, right. So, in this particular case, as per this particular example and also as that graph, almost everything rise there. Turbine efficiency also appears to be constant, right, because our low flows are less, but it is not the case always. Remember, if you selected Francis turbine, you can see it is different. You must have at least 0.2 or 20% flow to start the operation, right. So, below values you have to remove, and then part load you can see 0.4, efficiency is something like 60%, right, efficiency is 60%. Therefore, you have to put, if you selected Francis turbine at 0.4, percentage per flow is 0.4, this will be 60%, right, 0.6. Accordingly, you have to give the efficiency values, right, efficiency. Now, you can calculate, right, P turbine. At turbine shaft, what is the power available? That is our equation, right. Efficiency into, efficiency will be now generator and transformer has 0.94 into turbine efficiency is this cell into, that is efficiency, Q is this value, Q, rho we will 1000 we will take out and say this is in kilowatt, G 9.81, H is 194 net head in our case. Sorry, 194. I have typed here something wrong. See whether any typing mistakes, that is right. It is 0 because flow is 0, we will copy it all down up to here. So, it says 2898, our calculation earlier said 2900. So, we can round it over to 2900 if you want. Okay, so, this is the turbine. It is not really the turbine, it is really the P output, because we have already included efficiency of the generator and the transformer. It is the power output of the term at the terminals of the transformer, right. And then we can calculate energy for each day, that is power into power is, this is in kilowatt, right, this is in kilowatt, because we have taken that 1000 term away, rho has 1000, we removed it, and therefore, we say it is in kilowatts, right. Therefore, energy will be P kilowatt into 24 hours, right, 24 hours. Into 24 kilowatt hours into number of such days. Number of such days are the frequency, right. First one is 0 because there are no such data points, but other days there will be. So, this is coming in kilowatt hours. Okay. So, every day we know how many kilowatt hours have been generated as per this calculation, right. Then we can see the total, right. You can put it in megawatt hours if you want, if the large numbers are large, right. So, this is in kilowatt hours. So, then we can sum it up, say annual energy. See, now it is a large number, therefore, I will divide it by 10 to the power 6, last cell value I will divide by 10 to the power 6 to make it gigawatt hours. You can see 13.12 million units of electricity. Right. So, our project can produce 13.13 gigawatt hours, right, gigawatt hours. I just divided this by 10 to the power 6, otherwise the number is too big, right. So, 13.13 gigawatt hours, so 13.13 million units. So, if you are selling each unit at 10 rupees a unit, so every year you get 131 million rupees as income, right. So, you can use this number now for your cash flow calculation, and the project cost you have to estimate, then you can do a cost benefit analysis, right. Any questions? I think these are straightforward for engineers. So, I am just doing it for you just to understand, right. You can do much faster than me, we are much quicker in the keyboard and all that, not like me, right. And you can do it in smarter ways also, right, smarter ways, right. That is, we can even use MATLAB codes and all these things without doing all this the way conventional way, but you must understand the reality, how it is done. Then actual implementation you can use a modern tool and do it, right. I hope that you will do not get confused with this kilowatt hours and that I took away the 1000 from that equation. I am assuming that all these things are straightforward for your level of right competencies.
Hello, sir.
Hello, yes.
Sir, I have a doubt while taking the efficiency of the turbine. So you had said when we are going for Francis, is it all the same 0.9 or there a change in the efficiency that
No, no,
that column?
yeah, that I agree with you. It need not to be the same, but you know that as per this particular chart that I referred to, when you get the percentage, this is the horizontal axis, see flow rate as proportion of the design flow rate. Our design flow rate is 1.8. So, I calculated the column here, right, percentage flow column, that is flow, available flow divided by 1.8. Here cell is H5 divided by 1.8. So, here you can see our flow is 0, 0.12, 0.4, 0.68 and so on. But as per this particular chart, right, when it comes to 0.4, efficiency is already, when it comes to 0.4, efficiency is already 0.9. See flat, we are already in the flat region, right. That is why I put 0.9 as the efficiency, because we have selected the Pelton turbine. But if we had selected the Francis turbine, which is also possible as per the that turbine selection chart, in that case what you say is very correct. When it is 0.4, then efficiency is 0.6 only. Therefore, we should have here at 0.4, here this number should be 0.6 then, if we selected Francis turbine, and 0.68, at 0.68 we can see 0.68, 0.7 is here, 0.68 is somewhere here. In that case, Francis is having something like 85 or 86, right. So, you have to put the correct value here, right, at 0.68 percentage flow, it should be 0.86 or so. So, actual values you have to put, right. So, but here since the Pelton is already in the 0.9 region, that is why I put all these values 0.9. I was not very careful about these things, because there are no data points there, can the frequency is 0, right. So, there are no days when the flow is this small. So, we do not have to worry about that, we can start from 0.4, right. So, but as per this at 0.4, already the Pelton has 0.9, that is why I put 0.9, right. But here it is a little bit going down, therefore, if you want you can incorporate that also here at the last values, here maybe 0.88 or something, right. So, of course, you can make it more accurate by doing these things. Hope I answered your question.
Okay, sir. But while designing and purchasing, which one will prefer then, Francis or Pelton?
That depend upon your prices, choices, etc. Now, you must see how much they are quoting for the Francis unit and the Pelton units. And now, the Francis will have a little lower efficiency, no. Therefore, the total energy generation might be also, you can see there are 200 data point 200 days, the percentage flow is 0.4, right, and if the efficiency is 0.6 during those large number of days, your energy production will be hugely affected. Now, let us put it and see. I put it here this Francis turbine values, right, 0.5, 0.55 and 0.4, 0.6, right, at 7, at 7.7 it is about 84. I am putting approximate value, you can put the 0. We can get the exact values and put them here, and then let us assume the balance is correct, right, 0.9 and so on. Now, let us look at the total energy generation. It has gone down to 10.5. from 13.13, right. Substantial decrease in the annual energy production, right. So, if you go for Francis, your annual energy generation will be low and therefore, your income will be low, annual income. But if the total package price of the package manufacturer gives you for the Francis is considerably lower than Pelton, then you can still consider. That all depends upon your cash flow calculation, economic evaluation. So, you must do one cash flow evaluation with Pelton turbine and another cash flow analysis with Francis turbine, and maybe Turgo was also possible. Another cash flow analysis is Turgo. You must get offers for all three from the manufacturer, right, and then with certain assumptions you can get the civil costs also approximately done, and then total project cost, then do the economic calculation, but your annual energy generation for the three types will be different. Now, you can see this is 10.5, previously Pelton had 13.1, right. So, your annual income is going to be different and project cost will be different, because they will charge differently for the two turbine types. I hope I make sense to you. Did you get my point?
Thank you so much.
Okay, thank you. That is a good question. Okay. So, now we have converted it to Francis turbine, that is why these efficiency values are different now, right. Okay. Turgo turbine is not here, right, but you can look for a, if you are interested, you can look for a chart having Turgo as well. There are charts, there are plenty of these things available here as well as with the manufacturers. Here you can see, let us see what this manufacturer says, Turgo turbines. If you can remember the photos we looked at, can you be familiar here? Now, I find that this manufacturer in his website has put our plant. This is our Belhulwe plant, photo of Belhulwe plant, if you can remember, right. He has opted for that. I judge it from these windows, right, which we did. Yeah, okay. Any other questions anybody is having? I am just wondering here. Okay. I did not insert more complicated questions here. Now, if you go for 2 turbine option, right, 2 turbine option, then you can modify this table. You can logically think and modify this table and accordingly see how much will be the energy generation, right, if you have 2 turbines. And when you are opting for 2 turbines, turbine operation will also be different, right. Turbine operation will also be different. Let me explain it a little bit. I will take a blank slide and explain. Here, now you can see, now we have set the plant and plant is in operation, and we have 2 turbines, 1 megawatt into 2, right. Yeah, got to get it to presentation mode. Okay. And now you have 2 turbines, 1 megawatt into 2 turbines. Now, suppose you start to, now it is dry season and so you get the rains, and you start the plant, right. You start the plant, this is plant output megawatt or kilowatt, right. So, when you get when you have water, this is time. So, you start the first unit and load it. Up to 1 megawatt you can load 1000 kilowatt, right, 1000 kilowatt. Now, you find there are still more water available, right. Now, you have more water, right. Then you can what can do? You can start the second unit, right. You can start the second unit also, because first unit is now full load and second unit can be started, right. Second unit can be started. Now, how do you do that? How do you do that? Now, you keep this on 1000 kilowatt, the full 1 megawatt, and start the second one from 0. That is not the way. Then the second machine will run on very small flows, right. What we will do is, we will reduce this a little, we will reduce it to 75%, right, and then start the second machine, right. So, your total will be then increasing, right, because we reduce this one in order to start the second machine with a larger flow rather than starting with a small flow, right. And if there are still more water, we will take the second machine also, first machine also to the full load, right. If there is still more, this is maybe this is this, let us assume this is as 800. So, this may be 1800, and then you start the second machine also, first machine also to another 200 to make it 2000, right. So, likewise in operation, depending upon the type of turbines you have to optimize how it load and unload it. Now, when the water level goes down, right, how do you stop machines? How do you keep the machines in the best operation point? That depends upon the efficiency curve. So, we will try to keep together the machines in the better efficiency point in operation of the power plant. So, all these things will enhance the total power generation. So, accordingly you have to think about this when you have multiple turbines, how your plant generate electricity. Therefore, you can further increase the total by, right, optimally operating the two turbines and accordingly reflecting that in this Excel sheet, right, accordingly reflecting it in the Excel sheet, rather than saying one turbine until it is full loaded we take it, and then the rest of the water from beginning we load on to the other one. That is not the actual way of doing it. Otherwise, you will have a smaller estimation here. So, those I think fine points you have to do it with experience, and also you can logically argue, you all are engineers. So, you should be able to logically argue and arrive at various refinements to this calculation, right, various refinements to this calculation. And also now we assume the transformer efficiency and generator efficiency to be flat from no load to full load. So, you can think about that, if there is a substantial difference, you can incorporate those curves also into this rather than getting them as constant, and thereby making your calculation more accurate, right, making the calculation more. Now, here we assume only the turbine efficiency is changing from full load to no load, right, but for transformers and for generators also there will be a variation, right. So, if you want, you can accommodate that also, you can look for a generator efficiency curve, right. You can see whether anything is available. the capability curve. I want to capability curve is that Q1. I don't know whether this is the generator. I assume. Here, you can see. So, they are changing as per this chart. I don't know whether they are 100% right, and frequency versus load kilowatt, and whatever you can see they are not ranging from very low values, but can range from these are for different power factors. Blue one is the 0.8 power factor. Let us assume that one is the applicable. You can see it is ranging from 0.83. I think these are two small values. These 2.9 generators are more efficient these days. This curve cannot be true. They are in the 90, 95, 96 range, right. There are no 10% losses. Here this may be correct. So, these are in 97, 98 in that region, right. This is a wind plant efficiency now. That is why you know that using these efficiency curves from the net is quite dangerous sometimes. Let us look for a generator manufacturer. Hitsinger is good manufacturer. Alternator Hitsinger, that is a good manufacturer. We bought our projects from this manufacturer. You can see for the first choice for small high power plants, small hydros. I just looked at their brochure, but I don't know whether it has any efficiency curves. Here are some numbers which I cannot rate, right, but sometimes good manufacturers indicate their efficiencies, right. So, you can get the generator efficiencies and incorporate them into our Excel sheet if you are really want to make it more accurate, right, more accurate, and for the transformers also. Any other questions? Otherwise, we can wind up. So, I have given you some insight by you doing some hands-on work. So, that just by listening to me you will not acquire knowledge. So, you must do it yourself. So, this is an example. Now, you have the capability of identifying a site by looking at a contour map and then deciding a project, doing an approximate calculation, and from office even you can approximately calculate and tell and discuss a project opportunity, right. Of course, you have to visit the site as we saw in the pictures there yesterday during our virtual field visit, that you have to go to the ground, right. You can't do everything from office. Hydropower is in the jungles, right. So, you have to go there and erect the projects, right, construct projects, and also these all the measurements, estimations we have to get validated and confirmed by site visit, site measurements, surveys, etc. Right. Okay. If there are no any other questions, we will wind up our tutorial session here.
Sir,
Yes, please. Yes.
sir, I have one question regarding yesterday's virtual power plant. Is it okay? Can I ask now?
Regarding?
Yesterday's virtual power
Yeah, okay.
plant visit.
Yeah, you can ask.
Sir, like regarding the controllers, yesterday when we were showing the controller, there was a water controller thing which was given
Yes.
to the powerhouse. So
Yeah.
other than that, like for the voltage and frequency regulation, maybe if it is is it grid connected or islanded mode?
Yeah.
Yesterday's power plant, I didn't understand. I missed
No,
that point.
no. But this, I just spoke about the water level controller because it is important for the from hydropower engineer's point of view, keeping the water level constant in the forebay tank. There are many controllers in the control system of the power plant. There are automatic voltage AVR and
Okay.
various other governors and also various other controllers in the normal power plant. So, we did not go into electrical engineers details. So, all these
Okay.
controls will be there in a hydropower plant. So, we did not go to those details. We went to the design of a small hydropower project from a hydropower engineer's point of view. He will buy the entire package from a supplier and install there.
Okay.
It will include all these PLC. There will be a nowadays all are PLC control. This machine is starting, stopping, all will be PLC controlled, right? No human intervention, and so all these controllers will be there.
Thank you, sir. Thank you
Okay.
so much.
Okay.
So one more question regarding the maintenance, especially compared to other power plants, the maintenance of hydropower plant is very crucial.
Yeah.
So how do we look into that aspect?
Yeah, you know,
especially for a small hydro.
Yeah, small hydros, you know, these turbines and the generators are very reliable. Therefore, they will have very less maintenance, But of course, there are maintenance in the civil side. You will have to regularly clean and clear the canals, forebay tanks, etc. and look after your penstock without any corrosions and other things on one hand. But other than that, in a hydropower plant, minimum maintenance. But if you have inserted the gearbox between the generator and the turbine, gearbox has certain amount of annual maintenance, because gearboxes are, you know, not easy to maintain. You have to change oil sometimes as per the manufacturer's recommendations, and also attend to various other functionalities like replacements time to time, maybe not annually, maybe during certain periods. Gearboxes have more maintenance compared to other components. Other than that, I do not see much of maintenance in hydropower plants, other than if you have a good system, if you have installed good lightning arresters, surge arresters, good earthing system without getting damaged during lightning, in that case you will have less maintenance. But I have seen some plants getting you know, problems due to lightning, and even generators getting burnt. When a generator is burnt, you know, repairing is not easy. If you can't do it in your home country, you will have to send it back to the manufacturer, right. So, you will lose several months of generation. So, these are also considerations for putting multiple machines. When you have two machines, if one generator is damaged by lightning, you have at least have other machine to run, right. So, you have some generation. So, these are also, but of course, when you have double machines, you have excess cost, because double you need space in the powerhouse, you need two control systems, etc. But other than that, there are advantages also. So, maintenance in a hydropower plant is minimum, and compared to any other power plant, I would say. Even in a solar power plant, you have lot of maintenance. You have to wash the panels, right. You have to wash the panels, etc. It may be routinely every week, otherwise your generation goes down, and so on. But in a hydropower plant, you do not have such kind of things, but you have to maintain the equipment. For example, now you refer to the water level controller. sometimes because water level sensor is at the top part, forebay tank is in a hill, top part of a hill. So, they are liable to be attacked by lightning. So, I have seen some power plants where the sensors are damaged and they could not find replacement easily. Then there is no water level control. So, there is a man in the forebay tank keeping a walkie talkie. When the water level goes up in the forebay tank, he gives a call to the powerhouse, increase the generation. Therefore, somebody will press the buttons, right, press the buttons to open up the needle valve, right. You can manually do, manual options are always there, and then the water level comes down. When water level goes down, he gives another call by walkie talkie. So, you know that very difficult to maintain. So, 24 hours they have to do it if the water level control is not working. I hope I answered your question.
Yes, sir. Thank you so much. It was a very insightful session
Okay.
with good practical informations a lot. Thank you so much.
Okay, thank you. Thank you.
Sir, excuse me, sir.
Any
No.
other questions?
Sir, excuse me.
Yeah, your voice is very weak. Talk to the microphone.
Excuse me, sir.
Okay, tell
Can you
me.
able to hear?
Better.
Sir, can we predict the amount of power generation based on the availability of the water?
The question is not clear, my dear. I can't clearly.
Sir,
Yeah, tell me.
can we estimate predict the power generation based on the available source of water, sir?
Yeah, I think that is what we have done here. Now, depending upon the available water here in this column, we have predicted the amount of power we can generate, right. So, this water availability has been predicted by the hydrologist. He has said here, for example, there are 271 days with the flow in between 0.5 to 1.0 cubic meters per second in that range. So, this is the prediction by the hydrologist based on 30 years historical data, right, 30 years historical data. So, we our power generation we have predicted accordingly, power generation and the energy generation we have predicted accordingly. Now, incidentally you can see this 271 days our power generation is only 772 kilowatt, whereas our plant has a capacity of nearly 3 megawatt. So, it is running mostly on part load. That is why it might be advantageous to put two machines. When the plant will be then each machine will be running at maybe 90% efficiency, correct. So, the two machine option might be better for this particular flow regime. I hope I answered your question.
So can we implement the two basin concept here, sir?
Yeah, that can be done, yes, that can be done, but I do not have time to go that is a bigger calculation. So, I think you yourself can do it, put one machine and start the second machine after it, right. Maybe you can put 1000, if it is a Pelton turbine you can put equal turbine 1500 into 2, assume this 2898 is 3000 and put 1500 into 2 and take the first machine and go to the maximum power, right, 1500 and then start the second machine, right, start the second machine. Here you will have to restrict it to 1500, right, and then take the other machine from here point onward. Then your efficiency values will have to be again repeated. This will have to come again here, the second machine is starting there. Here, right, and then first machine ends here and second machine starts here, that is 1500 plus this point, right. So, your flow will be now not 1.72, it will be again starting from 0 or corresponding to the next step, right. So, this will be starting again from 0 for the first machine, right, and then again going ahead. So, you have to accordingly adjust your columns. So, second machine will be starting here and going, and then once the second machine also 1500, both machines will be in operation, right. That is how you do it. Then there are 3 machines, accordingly you have to adjust. I hope you can do that part alone, right. Okay, any other questions, or otherwise we can wind up here. We are nearing our session
Sir,
end.
can you
Yes.
share your mail ID, sir?
You mean my mail ID?
Yeah,
Okay, I can share. I will type here.
thank you, sir.
Yeah. Simple. Anura w@uom.lk. Can say, you are free, you can ask any question. If possible, I will answer if I know. This is my email number. If anybody wants to have an additional question, you might ask me. I will try to
Sir,
answer.
can you zoom it? Zoom it. It's not clear in the Teams.
Okay.
Can you
I will read
increase the font?
Yeah, Anura
Yeah,
w,
okay, sir.
Anura w@uom.lk. Okay, hope now it is seen. Okay.
Yes, sir. Thank you.
Okay. So, if you are in private companies, suggest to your or boss, your chiefs, if there are hydropower opportunities, why not we do it? If in your area, if there are hydropower opportunities. In India, as I said in the first lecture, as per the Ministry of Energy, there are 21,000 identified 21,000 gigawatts of identified hydropower opportunities, and about 25%, that is about 4,500 something like that, have been developed. So, there are large number of opportunities available in this country, which I think you should do, right, because there are environmental targets, net zero targets coming up, right. So, all these opportunities, while doing solar, wind, everything, hydropower also, the balance 75% must be developed, right. So, it will be good for the country and good for the planet also, if we go for more renewable, and hydropower is one of the best renewables, because intermittency is very minimum, right. Whereas, wind and solar, you have intermittency, seasonality, diurnality. Solar is diurnal, only say 8-10 hours of input every day, generation every day. Wind is seasonal. If you take 12 months, wind may be available 6-8 months. Balance 4 to 5 months, you have zero wind or very low wind. Therefore, you have to have some other power plants for the supplement. Whereas, hydropower is seasonal, of course, there are dry seasons, wet seasons, but other than that, steady power generation. Okay, thank you very much, and so we end our discussion here today, right. Okay, thank you.
Okay. So, welcome to this session tutorial 3. So, here I will explain one simulation, that simulation file and the simulation parameter file will be shared with you. So, accordingly you can run at your system and you can see the results obtained from that simulation file. So, before that I think is it shared now? Okay, after this after I explain, then that those files will be shared in MS Team as well as in WhatsApp group. Next slide. Okay. Okay, this I already explained in first class. Okay, so now today we will talk about this converter, power converter, and a part of this power converter, because when we are going to extract power from the renewables. So, as I explained for hydropower plant, we need AC to AC converter when it is connected to the grid. Here we try to configure it for AC to DC microgrid. Okay. So, here this could be the configuration. These two configurations need explanation. So, first is for solar PV, another one is for mini hydropower plant. Now, what you have here is, so in this figure what you have a DC microgrid for both the cases, then you have solar PV or you can have mini hydropower plant. Now, here sits the DAB converter, okay, dual electric bridge converter. So, before that let me explain you components one by one. Okay. So, here you see, when you have microgrid or any grid, that means what, this DC bus that we have here, this voltage is fixed or regulated to a certain voltage, okay, for both the cases. Now, this part is on the grid side or load side. Now, this side is the source side, So, whether it is solar PV, whether it is hydropower plant, as I explained in the very first day, that you have to extract power at MPP, So, since solar output is DC, so we are using a DC converter. When there is a mini hydropower plant, so you have AC here, then AC, and then here you have DC. So, there is a AC to DC conversion. So, here also it is DC to DC conversion. Now, for power to be extracted at MPP, the criteria is this DC link voltage must be regulated. Okay. Now, when it is connected to when this when this mini hydro power plant I explained connected to AC grid. So, we had configuration, if you do not remember, let me draw it once again. So, what we have is, we have the machine, then we have back to back converters, and then you connect it to the grid. So, this is AC to DC, this is DC to AC. So, this is grid and this is the machine, induction generator, or sorry, this converter fed synchronous machine. Now, here I told you that this converter will be doing MPPT and this converter will do DC link voltage control. Okay. MPPT and DC link voltage control. Now, here instead of grid what we have is microgrid, where the voltage is DC voltage, and also this voltage is substantially low compared to the voltage for mini hydro power plant, or this is not same as this voltage. These two voltages are not same, and this voltage I told you that this voltage could be higher voltage and DC microgrid voltage will be comparatively much lower. So, there is a voltage mismatch between these two ends, voltage mismatch between these two ends. So, if you remember, for back to back converter connected to the grid, we had transformer to match the voltage. Okay, we had transformer. Here we do not have any transformer. How to do that? Okay. So, configuration that we try to achieve here is let us say if it is a mini hydro power plant, then this is the source, then we have AC to DC converter, the DC link voltage is generated, then there is a DC DC converter, and then it is connected to the DC microgrid. Now, what could be the problem here? If you use a DAB, what, or in this configuration, what is the challenge? What is the challenge that we have? Anybody can tell from offline online participants? What could be the challenge? You just see this image, see this configuration, and you tell me, you just try to figure out what could be the issue. If we use so instead of back to back converter connected to the grid, instead of this, so here this DC link voltage was fixed or regulated through this converter, and this was MPPT was done by this, and this is only achievable when this DC link voltage is regulated. So, we need to regulate this DC link voltage, and this is already regulated as it is a DC bus voltage, DC bus of a microgrid. So, this voltage is to be regulated. Previously, it was a back to back converter from the grid, we can able to regulate it. Now, we have a DAV DC DC converter. Now, DAV converter cannot regulate DC voltage, this output DC voltage, if it is SPS. Okay, that I will come to, I will come to that. Okay. Now, so that means in this configuration, this will do MPPT. So, this is this one, this converter is this one, MPPT. Then you have a DC DC converter which will control the power flow, which will allow the power, the maximum power to flow and to the DC microgrid. Now, the two things that you need to think of is how to regulate this DC voltage. This DC voltage is already regulated, and there is a power flow which will depend on phase shift angle, external phase shift angle, power flow, external phase shift angle. So, it depends on external phase shift angle. So, MPPT power is generated, that is that control that I explained in first lecture, that that rotor speed control will be done, and the DC link voltage has to be fixed. This DC link voltage in this configuration has to be maintained using this DC DC converter. How that you think, how it can be achieved, that the DC link voltage you want to maintain this, so voltage control. So, you must to have a voltage control, the control, it has to be, the DAB has to be in voltage control mode, so that this DC link voltage can be maintained at a fixed voltage, and at the same time you do this firing angle, external phase shift angle control, so that power can be delivered to the DC grid. Now, the question is here, since it is mini hydro or solar PV, whatever it is unidirectional in nature. So, power only flow from source to the load. Here also power flows from source to the load. So, you might not need two active bridges, active bridge here, active bridge here. But the question is, when you are going to regulate this DC voltage, when you need to regulate this DC voltage, you will see you need to have a bidirectional power flow. As I already explained yesterday, when it is a DC DC converter and it is going to maintain the any DC bus voltage, it has to be bidirectional in nature, otherwise that that cannot be achieved. Okay, is that clear? So, now with that if it is so in addition to this, just let me explain you another converter where you have similar kind of DAB converter kind, but it is not dual active bridge, it is single active bridge. So, what you have here is so this is an active bridge. But this is a diode bridge. So, as I told you, when it is diode, it is always power flow in one direction, it is in from this side to this side. This can also be used, but since you are trying to maintain DC voltage using this converter, it is using this diode bridge rectifier will not do. So, what you have to do is you have to use a dual active bridge converter, and you have to see, you can think on it how this DC link voltage can be controlled, so that MPPT can be achieved and that MPPT power can be delivered to this DC microgrid. Any query from anyone online and offline, I will address it, because understanding this configuration is necessary. Okay. So, today in simulation what we have this DAB DC-DC converter, we have this DAB DC-DC converter which you can run using any of the modulation techniques that I explained yesterday, SPS, EPS, DPS and TPS. Okay. Okay, so this is this configuration I have in my simulation. So, here you have DC voltage input, DC voltage output, battery is the output connected at the output. There is a high frequency transformer link, there is an active bridge here, active bridge here. Okay, so using this modulation scheme you can run the DAB converter, and then you can see in which modulation scheme you can able to control or maintain the output voltage here. So, here if you see here what we have, this is a battery. So, battery charging can be done using two methods, CC and CV, constant current charging, constant voltage charging. So, constant current charging is like irrespective of battery voltage, you are pushing a constant rate current to the battery. It could be, so if it is a DC fast charging, it is almost like 120, 1.2 C or 1 C, something like that. The rate is like that. So, you charge at constant current up to 80% of SOC, and then you move to, otherwise if you continue it, then the battery could be overcharged. Okay, so 80% of SOC, and then you move to constant voltage charging. So, how you can achieve this constant voltage, that you need to see whether it is achievable using SPS, EPS or DPS, that can be done or not, that you can see. Okay. So, this thing I already explained, SPS, EPS and DPS. So, in SPS the internal angles, so these are the internal angles, internal phase shift angles which are 0 for SPS. So, in the simulation model that we are going to share, there this you can adjust both alpha 1, alpha 2 and alpha 3, all these angles you can adjust and you can accordingly you can get the results. So, alpha 1, alpha 3 will be 0 for SPS, and you play with alpha 2 and see the power flow whether it can be achieved or not, and also you can see whether there is negative, that I talked about back power flow. I talked about, you can see whether the back power flow is there or not in SPS, and also how this back power flow can be minimized in EPS. In DPS you can see whether this constant voltage charging whether we can achieve or not, and then TPS where we have both internal phase angles are not, internal delay angles are not same, and there is an external phase angle as well. Okay. Now, these are the simulation parameters. These simulation parameters are mentioned in this simulation parameter file that will be shared with you, and this is the DAB converter simulation file. There you have the DAB converter where you can control the phase shifts. This phase shifts, variable time on transport delay block is there. These blocks are there. By adjusting the angles here, time delays here, you can adjust both alpha 1, alpha 2 and alpha 3, and accordingly you can achieve SPS, EPS, DPS and TPS. So, simulation parameters are here also, it is given the same simulation parameters, and then this file will be shared. So, what you have to do is you run the, so all of you, we assume that all of you have MATLAB. I have saved this MATLAB file in a lower version of MATLAB, so that irrespective of if it is typically some recent MATLAB version that you have, then also you can run it in online also. I do not know whether this time step will be, you have to keep time step 10 to the power minus 6 or so. Okay, acha. One thing I supposed to tell you that I personally prefer you always run MATLAB in fixed time step, not variable time step, and the time step TS generally I prefer e to the power minus 6. For DAB we are running at 1 e to the power minus 7, though it is taking huge time. Okay, this you can try 10 to the power minus 6, you can try time step fixed time, but you run it at fixed time step, this I prefer always. Okay. Now, for your reference, what we did is we have kept the waveforms. So, how the SPS waveform will look like, how EPS waveform will look like. Okay. So, here you see in SPS waveform both are square wave. So, since both are square wave, that means here that delay alpha 1 comma alpha 3, this you make 0 and then you run it and then you will get the result. You run it for different value of alpha 2 external phase shift angle. External phase shift angle. You run it for different values alpha 2 and see how much is the power flow, and this is the power flow waveform that you will get in SPS with some negative. So, these things you have to observe. Then in EPS, if you run in EPS with alpha 1 not equals to 0, alpha 3 equals to 0. So, that is why the secondary voltage is a square wave, primary voltage is a quasi square wave, and then you alpha 2, then you play with this and you get the result of output power. In DPS what you do is, in this is EPS, another waveform EPS, then in DPS, so alpha 1 equals to alpha 3 not equals to 0. So, this internal phase shifts are there for both the phasors. So, you can see here when you are doing, so this is when alpha 1 equals to alpha 3 equals to 0 for SPS. In DPS what we do is we introduce some delay. So, if you introduce some delay, then it will be a quasi square wave. So, the waveform will be shorter, but this will be same for both of them. So, these phasors are going to be shorter for both of them. So, this angle is alpha 2. Okay. So, this is SPS and this is DPS. Okay. So, here we introduce internal phase shift to both the bridges and it is same. So, this is the inductor current, this is DPS, another waveform TPS. This is TPS. So, in TPS now the degree of freedom is much more. So, previously in SPS we had two phasors like this. Okay. And now since alpha 1 not equals to 0, alpha 2 not equals to 0. So, this is alpha 2 and then alpha 3 not equals to 0, but alpha 1 not equals to alpha 3. So, in this case, so this will become somewhere here, let us say this VP phasor, this VP dash now, and this is VS phasor, Now, since alpha 1, alpha 3 are different, now in this figure you see here it is less, it is more, that means this will be smaller in length, this will be smaller in length. So, in that case it is previously when it was DPS, EPS, sorry, yes, when it is DPS it was equal, but here it is not equal. So, Vp dash, this is Vs dash, okay, and this is alpha 2. So, these things you run the simulation and check whether you can achieve these things or not and how it is affecting the power flow. Also you have to comment on, so that will be an assignment that you have to submit. You have to comment using which modulation scheme this can be achieved, this can be achieved, in which modulation scheme this can be achieved. That assignment, a write up that you have to submit with your comments, that how, which modulation scheme it can be achieved and why do you feel that okay, this is the particular modulation scheme by which we can do this. Okay. So, these two things you have to write and submit same as like previously that you have submitted. Okay. So, now I explain the things. So, now you can share the two files, you share to WhatsApp group as well as in MS Team. So, everybody run those simulation and then if you have any doubt, so after let us say, so this is 3, after 15-20 minutes we can again discuss the same thing and then so 3:20 will start again, and if you have any doubt, otherwise if you have no doubt then you submit the assignment. So, this will be assignment 2. Acha, one more assignment I will give you, that will be based on the first lecture that I gave, that I will write and give it to the MS team, and that also it will be a small write up that you have to submit. Okay. Okay, then we are stopping here. Reference waveforms are here available, reference waveforms are available here. This PPT we can share in the MS team for their reference, this PPT, so that these waveforms they can see and they can accordingly they can execute the simulation file. Okay. So, if you have any query, let me know. Otherwise we can stop here and we will start again at 3:20. Can we start now? Okay. Okay. So, welcome back. So, hope you all receive the simulation file as well as the parameter file. So, first of all there are 4 simulations, it might take time to execute each and every one and to see the performance. First of all, if you face that you are not able to run the simulation file, then you let us know, and if you are able to run it and if you have any query, so that so here this one is alpha 1, alpha 1, alpha 2 and alpha 3. Okay, I forget to mention it. So, by adjusting this, so for SPS you make alpha 1, alpha 3 0 and then you put some alpha 2 and execute and see whether this result is coming or not. This result is coming or not, and then again you put alpha 1 not equals to 0 here, alpha 1 not equals to 0, alpha 3 equals to 0 and see whether it is running or not. So, this session I again resumed in order to know that whether you have any query, any doubt, anything that you have. Okay, we forget to share this, I think this PPT we forget to share, right, this PPT. So, this PPT we will share, this PPT will share, so that you can take for reference. Please share this PPT. Okay. So, I am here, if you have any query regarding that simulation running and any other issue, please let me know. Reference waveforms are mentioned in this PPT, that you can see, that PPT will be shared soon in MS Team. also I posted one assignment. That assignment by today night you write on a paper your justification, then you scan, upload. It could be soft copy, it could be handwritten also, no problem. Okay, so just you think on your side, think, justify, and then you write your answer and upload. Because this MPPT tracking and connecting to the grid is a typical problem. This is a problem in the sense of there is a typical application where what we do is we extract power at MPP and then feed to the grid. Very rarely means there are chances when we work in islanded mode. So, let us say you have a solar inverter. So, let us say you have a DC-DC converter, boost converter, after that you have a solar inverter. So, that solar inverter is feeding power to the grid, and when it is connected to the grid, it is in current control mode. When it is islanded mode, then you have to give some voltage reference and frequency reference in order to work it in standalone mode. So, understanding this is essential actually. How with different, there are papers which explain this phasor diagram, first harmonic phasor diagram, that is explained in many paper. Many paper means at least I went through 4 papers which explain the how you can deal these things with the phasor, because phasor is the best thing to understand when it is AC. So, here it is high frequency AC. So, the best part is by doing this different modulation scheme, by employing different modulation scheme, and then you try to understand from this phasor diagram point of view. Here this side voltage is fixed and you have to keep this side voltage fixed. PPT is shared. Okay. So, PPT is available, you can see for your reference. The reference waveforms are given. So, you run the simulation and you can compare with the result that you obtain from the simulation. Now, you can see that there you can play with the angles. It is in open loop mode. In closed loop, you have to control this EPS modulation if is let us say. Then the duty ratio, inner and outer phase shifts you have to control in order to control both the back power flow as well as the power flow from one side to other side. So, after this session from 3:45 next tutorial session will start. Okay, so participants will run these files and they will try to see the performance of different modulation scheme. So, we will stop here, we will stop this tutorial 3 session. Thank you. If you have any query, you can post your query in the WhatsApp or in the MS team that is created. So, we can address those issues whatever is there with this simulation. Okay. Thank you.
In my last lecture, I discussed about the overview of microgrid and the energy storage unit and the design means the sizing analysis of energy storage unit. And in that lecture, I told you about this there is a box, black box, which is a power electronics converter, but I have not discussed anything about the power electronics converter used for this any of the component, and some of the power electronics converter is already discussed by Professor Sarkar for the source, means mini hydro power plant design and its corresponding power electronics converter is already discussed by Professor Sarkar. But in my today's lecture, I am going to discuss about the power converters that will be used for the energy storage system. So, when I am talking about the energy storage system, I will be talking about the different types, means I will just scroll down the types of the power electronics converters, but my main focus will be on the design of this power electronics converter which will be used for this battery energy storage system basically, and its simulation. So, these two are the main focus of this today's lecture. So, I will be doing I will show you the simulation steps, and finally, I will give you the Simulink model for it. So, to start with, let us talk about the power electronics, that is converters, that is going to be used for this energy storage applications. And already in my last class I have focused about this electrochemical energy storage that are being used for a standalone system. It can also be used for grid connected applications. But how to choose whether depending on if you are integrating the power electronic storage, energy storage with the corresponding grid, if the grid is AC or DC, depending on that you have to choose two types of power electronics converter. That is, if you are connecting to the AC source or AC grid, then you are going to, because the storage side it is the DC fixed. So, either you are going for a AC to DC converter, or if you are integrating with a DC grid or DC microgrid, you can say microgrid, then you are going to use a DC to DC converter. So, these are the types of power electronics converter broadly we are going to use for when we are going to interface the storage, energy storage system. And when I am talking about the energy storage, basically we are mainly focusing on this electrochemical storage, and where we have discussed about these two storages, that is the battery and supercapacitor, which is having the complementary characteristics. This nowadays it is mainly used for this microgrid applications, battery which is having high energy density and the supercapacitor which is having high power density because of their complementary characteristics. So, these batteries can be used for the steady state application, and for transient application we are using the supercapacitor or the ultra capacitors in the microgrid application, so that it reduces the size of the battery. So, that is the type of storage that is being used in the energy storage side. So, but apart from in between these two storages, I am not talking about the hybrid energy storage here, I am talking about only the single storage, and that too, that is the battery energy storage system. So, I am talking about the sizing of this battery I have discussed in my last lecture. So, I will talk about now the accessories or the intermediate stage which will be there as a power electronics converter, so that we can interface the storage with the grid. The grid can be AC or DC. So, and it has to operate bidirectionally. Why bidirectional operation is needed? Because when I am interfacing a energy storage to the grid, so the grid can be AC or DC, that is separate, but the bidirectional means depending on the source, if you have a excess of energy, if the generation is more, then we have to store it. So, the battery has to, or the energy storage system has to absorb the power, or it has to store the power, and when there is a deficit of energy or deficit from the supply, then and load is more, so then we need to, the battery has to supply or it has to discharge. So, in that case, so we need a bidirectional operation. So, we have to choose the power converter so that it can operate bidirectionally. So, this is the and we are mainly focusing on this microgrid or this grid applications, and I will just talk about the different types, which there may be some overlap with Professor Sarkar, but I will show you the names here. So, for the while we are going to interface the power electronics converter with AC grid or AC bus or AC microgrid, you can say anything, AC microgrid, then we need a AC to DC converter, and the types are broadly boost type, buck type, buck boost type and multi-level type. multi-level type sir has given some idea on it, and this boost, buck and buck boost type for this 3-phase AC system. When this is the grid, we are interfacing with the energy storage, which is DC. I am interfacing this. So, in between we have different topologies. So, this is the topology for a bidirectional boost. So, power flow is possible bidirectionally. Okay. The grid can supply or grid can take, or the energy storage can be charged or it can be discharged. So, we need this bidirectional converters. So, the switch has to be operated bidirectionally. So, it must have its body diode or the feedback means internal diode, so that it can operate bidirectionally. So, here in the bidirectional boost type I have shown here 3 topologies which are available in these references. So, you can go through it. So, one is bidirectional 2-leg, first one is the bidirectional boost type 2-leg converter. So, we have 2 switching legs here. So, you can see it clearly. So, we have 2 legs here and 3-wire system, and this is the topology with 3-leg 3-wire system, and this is the topology boost type, bidirectional boost type and 3-leg 4-wire system. So, these are the topologies for which are used for this AC to DC converter as the AC to DC power electronics converter, and then in the buck type there may be some other topologies also, but I have shown some topologies which are normally in use for this to interfacing this AC grid with the energy storage. So, this is the buck type topology where you can see that there is a LC filter in the output, and so this topology is having a 3-leg as well as 4-leg structure. Okay. This is a 3-leg, it uses 3 legs, and for high power the switches can be GTOs, and for low power applications the switches can be IGBTs. So, this 4-leg topology is advantageous because it reduces the DC link voltage ripple, and also for balancing currents in case of the unbalanced supply system. I am just giving you just the overview of the AC-DC converter, bidirectional AC-DC converter that is being used, and some standard topologies. So, this is another type, that is the third one, that is the bidirectional buck boost type, where I have shown only 3-leg structure. Okay. And the fourth one is the multi-level type, where we have different topologies, again multi-level diode clamp, flying capacitor and cascaded, and obviously you know the advantages of multi-level topologies, why and when we are going for this multi-level operation. So, when in multi-level converters we have the advantage of better power quality, that is the lower THD, lower EMI, electromagnetic interference, and it gives better power factor or higher power factor. So, this is about the AC to DC converter topologies we are using for this for interfacing between the microgrid with the energy storage system. Then our main advantage means our goal is to talk about this DC to DC converter interface. So, we are integrating this with a DC grid, in between DC grid and the battery energy storage system. So, battery energy storage means the battery, the energy storage unit along with the power electronics converter forms this battery energy storage system. So, here also there is a overlap, that is the isolated type and non-isolated type, and isolated type is already greatly means in detail it is discussed by Professor Sarkar. So, and here are the applications I have mentioned, that is for the this DC to DC converter we are integrating DC grid, and in between the DC grid and base we are putting this power electronics interface, which is a bidirectional DC to DC converter. Before coming to the topologies used for this DC to DC converter, for the DC to DC converter the applications are already we are discussing, that is DC microgrid means the renewable energy system integration. So, when the source is having DC and the storage is obviously DC. So, we are going for this application. Another is the interface between the again the DC link and the ESS, that is the line interactive EPS. And the most important apart from the this microgrid applications, nowadays the important another factor is the EVs, which are means for EV battery charging. I am talking about the energy storage, which is used for in the microgrid for the storing the energy, and it will EV will be as a load. So, that is also used with, means that is also another application where we are using these bidirectional power electronics converters. Okay. And so, this is the already today means just half an hour before you have discussed, sir has done I think simulation also. You have discussed the modulation techniques, the details of DAB, the dual active bridge converter, which is nowadays very much used for this microgrid applications. So, this already covered. So, I am not going to talk anything about it. So, now the main thing comes here, the non-isolated one. The non-isolated one is the between the DC grid, that is I am putting in between the DC grid and the energy storage unit. So, I am putting the this DC to DC bidirectional, that is BDC, okay, between the DC grid. And so, here the topologies which I am not going to explain, I am discussing that one first, that is the Chuk converter and the SEPI converter, which are also used. These two converters uses two actively active switches, okay, and there are the filter, all other filter components. So, components are more. The advantage is it gives low ripple input and output currents compared to the other one, but the number of components are more, and it uses two active switches. So, and also gives a high voltage conversion ratio. Okay. So, this is the advantage, whereas the main drawback of this Chuk converter and the SEPI converter are it needs a large inductor and high voltage rating capacitors, as it gives a higher voltage conversion ratio. So, we need and also higher current stress on active switches as well as on diodes. Okay. So, this is the two topologies, these are the two topologies which are used, but having these disadvantages. So, the most commonly used and simple configuration having the advantages is the half bridge topology, which use a single leg, okay, single leg, and the number of passive elements are less compared to the Chuk and SEPI converters. Okay. So, that is the advantage we are seeing here, and here for this converter I will talk about the its operation first, then how to design the filter components for this converter, okay, and then its controller used to have, means if you are operating in a closed loop control system, then how to design the controller for it. Then I will see the simulation of this non-isolated bidirectional converter, NBDC, NIBDC or NBDC, in different names it is you are using in short forms. Okay. So, if you will see two switches here, one is the upper switch and you can say it as a lower switch. You can check properly, there may be some mismatch in the naming, you can adjust it, but it is all the same. So, top switch, bottom switch also you can say. Okay. So, it can operate. So, here as it is operating between the DC microgrid and the energy storage. So, it is operating bidirectionally, that means when there is a excess power or excess generation, then the battery will charge, means it takes energy, and when there is a deficit generation it delivers, the energy storage delivers. So, based on that either it will operate in a boost mode or buck mode. So, based on that also this bidirectional converter is also called bidirectional buck boost converter also. Okay. So, this topology how it is operating, that will see, and with that single leg, if we will add more legs, so to get some more advantages for some high power applications, we are going for two more topologies, that is called, one is a cascaded half bridge converter topology CHB, and this one, the second one is the interleaved bidirectional converter topology. Here only two legs are shown, this can, there can be multi-phase depending on your current requirement. Suppose you are going for a 100 ampere application, so you can go on adding more number of phases, obviously more number of phases, more switches. So, complications or complexity is increasing, the control complexity, operation complexity, so those are increasing, but the advantage is it will minimize the inductor current ripple, and also as current flowing through the, as you are dividing the current for this interleaved topology, so the size of the inductor will also decrease. So, we can have a better modular structure. Okay. So, based on different applications, we can go for this interleaved topology or the cascaded H bridge topology. Okay. So, I have just given you the various topologies available in literature, but now we will focus on the simplest one, the converter having a single leg. Okay. The top switch and bottom switch, based on that I will talk about the how the means the operation of the bidirectional converter, how the converter is operating when whether the energy is stored. Here I have reversed the direction, here this is the battery and this is the bus. Okay. In between we are using this bidirectional converter. Okay. So, the load is, the DC load is connected to the DC bus. So, this it is having the filter components, you have the input capacitor and output capacitor filter and inductor filter. So, you have to, after understanding the operation of it, we will try to do the design of the filter circuit first, means the converter design, when we will say means the designing the filter circuit for this converter. Okay. So, first let us give me means it is operating bidirectionally I told. Okay. So, in case of boost mode means the it is operating in discharging, means battery discharging mode. Okay. So, which switch is active in this case, and we have two active switches SB1 and SB2, okay, and the corresponding body diodes DB1 and DB2. Okay. So, when the switch for the boost mode, this SB1 is operated. Okay. I will show you in this in a better way here. Here if you will see the bidirectional converter during boost mode of operation, okay, and this is the equivalent circuit when switch this SB1 is on. Okay. So, during the on period of when the switch SB1 is on, so this is the path, means so inductor stores energy, okay, and the diodes DB1 and DB2 are off and switch SB2 is also off. But the how the, so here VDC it is connected to the load is connected here. So, at that time this capacitor supplies to the discharges to supply to the load. Okay. So, inductor stores energy during this, means when the switch SB1 is on. Okay. And in this case, to calculate the filter inductor, so we will use the volt second balance technique. By using the volt second balance technique, you can see the voltage across the inductor, let it be VLB. The switch is on. Okay. So, what is the equation? The voltage across the inductor is equal to the battery voltage. Okay. And what is the voltage across inductor? It is L di by dt. So, using that you can do this LB into di is the del IB the current ripple, and the dt is the on time of the switch into the time period. So, using that you can find out the corresponding inductance value or the filter inductor of this bidirectional converter operating in while during the bush mode. Okay. So, this is you can try, this is the standard one. So, for other filter components also you can find out. For the capacitors you can use the what is required to calculate capacitor, that is the ampere second balance technique you can use to calculate the input and output capacitances during buck mode or bush mode, that we will see. So, this is about the bush mode, means when switch is on, but when the switch is off, in the next slide I have tried to show the bush mode of operation means battery discharging, but the SB on is turned off. So, at that time, so here actually basically in the previous case you can see the potential of this means power means the switch is on, okay, and here in the after you are turning off the switch SB1. So, this switch is on off, SB1 is off, and you have not given pulse to SB2, okay, and DB2 is also not conducting. So, where the inductor is storing charge and suddenly you cannot break this current. So, what will happen? Now, current will flow from the means the current stored in the inductor will now discharge through this body diode of the upper switch. Okay. So, that is the battery discharging, means it is now supplying to the load. Okay. Switch is off, means all the three components SB1, SB2, DB2 are off and DB1 is on. So, like in this similar way you can do the analysis for the buck, means just reverse direction power flow, means I am just so here I have shown in detail. Again you can draw the corresponding circuit for to, so the means buck mode of operation when the upper switch will be operating and the lower switch is off. So, in the boost mode the lower switch is operating and the upper switch is completely off, and so it is in the when the switch is on it is conducting, means inductor stores energy, and when the switch is off it is flowing through the upper switch body diode. And but reverse is the case when we are going for the buck mode, that is the battery charging operation, means from the power will come flow from. So, here do not go by this, means this switch will be on and this will be kept off. So, when this switch is on, so it will flow in this way. So, inductor will store energy in the reverse direction. So, that is the battery charging mode, and when this switch SB2 will be turned off, the opposite will happen, means it will flow through the DB2. So, that is the buck mode or the battery charging mode operation. So, first one I have told boost mode or battery discharging, and so similar way you can draw the its equivalent circuit and do the analysis, and finally you can find out the corresponding filter capacitor components. So, now this is about the circuit operation, and now coming to the controller that is being used for this bidirectional converter. So, we are operating in two modes, already told, buck mode and boost mode. So, based on that we can have the we can generate the duty cycle so separately. So, that is called the separate controller approach. Okay. Separate controller approach means here from the we have the controller circuit. So, where the power management will generate the reference currents, and the reference current command will again further give the generate the duty cycle to means buck mode means battery charging, it is flowing in this way, and the boost mode means battery discharging, it is flowing in this way. So, it will generate the duty cycle for the upper and lower switches separately. So, that is why it is a separate control approach, which is normally we are going for going to use this what is called unified control approach, okay, where the controller I will come to the controller, I will show you the what is the control approach. So, here the controller will generate the duty cycle, means when the upper switch is on, it will upper switch is on means which mode? Buck mode, load switch. So, it will give a pulse at that time, the inverted pulse will be generated or given to the load switch, means when this is on, means they will operate in a complementary fashion. Okay. So, that is generated by this unified controller, and what is there in the unified controller, that we will see. So, now coming to the bidirectional converter. So, after this again we will go back to the converter, but before sorry controller. So, before going to the controller design and its simulation, we will see the design of the filter components. Already I have told what to means from the different operating modes, means whether it is a buck mode or boost mode, you can get the corresponding inductance and the filter inductance, filter capacitance, input capacitance and output capacitance value. So, let us design for taking a power rating of 1 kilowatt. Okay. So, the load it is based on the load, actually we are deciding the power rating of the DC microgrid. So, and we are fixing the switching frequency, let us take it as a 10 kilohertz, you can go for 20 kilohertz also. So, and we are fixing the battery, we are choosing the battery voltage, and here for the DC bus of 48 volt, where I am saying it as a normally LVDC microgrid. So, we have chosen a battery of input voltage of 24 volt. Okay. And already I have told the output voltage is 48. So, as the power rating of the load is fixed, the output voltage and input voltage, this is the battery voltage and this is the bus voltage. Okay. So, the battery current, the maximum battery current can be, we can get by the load power divided by the battery voltage. So, the maximum battery current it has to be designed is 41.66 ampere, this 1 kilowatt load divided by 24 volt, and the output current, when I will get the, that is the output voltage is fixed to 48 volt. So, the output current we are getting nearly 21 ampere, 28.83, you can check it. And so, we have to fix the battery ripple current. So, this ripple current we can be considered between 10 to 30%. Here in this example I have chosen 10%, okay, of the maximum converter current of the input side. So, battery current we have calculated 41.66. So, 10% of which the ripple current of the battery. So, that is 0.1 of the 41.66 is 4.166 ampere. Okay. And the battery voltage, if you will see, the battery voltage ripple can be also designed for 1 to 2%. Okay. And for this example I have chosen the battery voltage del V as 1%. So, based on that the input voltage ripple is fixed to 0.24 volt and the output voltage ripple is fixed to 0.48 volt. Okay. So, this is the we have calculated the maximum input current, the load current, the input current ripple and the input and output voltage ripples. So, now we have to find out this LB, the filter inductor and the filter capacitance values input side and output side one by one. So, this is already in this while discussing about the operating modes, I have shown you the, this is the standard one, any reference you can follow to find out this filter inductance and using the volt second balance technique. And here as all the values are known to us, the switching frequency is 10 kilohertz. So, this is the filter inductance is found to be 0.288 means nearly 0.3 millihenry. Okay. If you will put the values you can check cross check the calculation, okay. And already using this del I 10% of the maximum current rating. And for to calculate the input side capacitance CB, it is required to find out the voltage, take the voltage ripple of the that is during the charging of the battery. So, charging of the battery means during the buck mode of operation. Okay. And using that ampere second balance you can calculate the capacitance, that is found to be 200, just put the this formulas are given here del IB into TS divided by 8 into del VB. Del VB we have calculated 10%, sorry 1% of VB. So, this is 0.24, and if you put all the values, this switching frequency is 10 kilohertz. So, we are getting a capacitance, input capacitance value is 217 microfarad. And correspondingly for the when we are calculating the output capacitance value, we can do it by during the battery discharging mode, and this is the corresponding formula, and the output capacitance value is calculated to be 2170 microfarad, nearly 2200. The standard capacitance in market we are getting 2200 microfarad. Okay. So, this is the all the filter parameters we have calculated. So, I will give one assignment on it. Similar way, means I will just the battery voltage will change, switching frequency will change, and you have to calculate all the filter parameters. Okay. So, after the class I will post in the group. So, then now you can operate this converter in open loop mode also, means you can give a switching pulse, okay, of any duty ratio, but what is required? We have to regulate this DC bus voltage. Okay. So, for that we need the closed loop operation is very much required, and directly I am going to the closed loop, means using this dual loop control strategy. You can have a single loop also, only using the voltage control loop, but directly what we are using the final result I am showing you, which will give a better performance. So, here the dual loop means we have a outer voltage control loop, inner current control loop. Okay. The outer voltage control loop generates the battery current reference command, okay, and when it is compared with the actual battery measured current and given to the PI controller, it generates a duty cycle. Actually, this will be to limit the duty cycle. The duty cycle, the practical limit will be between the you cannot vary from, though we are saying that duty cycle can be varied from 0 to 100% or 0 to 1, but practically it is better to use between 0.1 or 0.2 to 0.8 or practical use 0.9 value, means 10% to 90% or 80 to 20% to 80% of the. So, here we are putting a limiter here, and I have missed one thing here, the current limiter also. Sorry, this is the current limiter, and this will the output will give you the duty ratio, which will be given to the PWM generator, and here we will set the switching frequency of this PWM, and it will give two pulses, means one actual pulse which will go to the switch SB1, okay, load switch, and the other one for the unified control approach. For unified control approach, it is inverted and given to the upper switch. Okay. So, this controller design and the PI controller tuning is the important factor before going for the simulation. Okay. So, how to design the PI controller? These are also very standard stuffs. Okay. Using the small signal modeling analysis, you can find out the control to inductor current transfer function and inductor current to output voltage transfer functions, and using the Bode plot analysis, you can fix the phase margin to 60 degree, and the here between this I forgot to tell one thing, the current loop, between these two loops which one is faster? The inner current loop is much faster compared to the outer voltage loop. So, first we will find out the bandwidth of the current loop and corresponding PI values. Okay. Then we will design the PI values for the outer voltage loop. So, the phase margin for both the loops are fixed to 60 degree, okay, to have a stable operation, and the bandwidth of the current loop is, as the switching frequency is taken as 10 kilohertz, it is 1/10 of it. So, we are fixing the bandwidth to be of the current control loop, which is faster compared to the voltage control loop, is 1 kilohertz. So, as fixing this, for the outer voltage loop, the bandwidth is almost 1/10 slower. So, the bandwidth of the voltage control loop is fixed to be 1 kilohertz by 10. So, it is 100 hertz. Okay. So, using this and after doing the some tuning for the parameters KPKI parameters for the outer voltage loop and inner current loop is found to be this. So, Kp for the inner current loop is 2.3 and we will use these parameters to do our simulation. So, this is about the first part, means when we have designed the converter and we are trying to putting all these values, we will do the simulation. So, here the battery voltage we have fixed to 24 volts. So, market available battery is 12. So, we are using 2 lead acid batteries, means in our use we have actually taken 12 volt 2 lead acid batteries which are connected in series. Then inductor we have calculated 0.2 something here, 0.288 nearly 0.3. So, standard we have little higher value we have chosen 0.5 millihenry and the nearly 50 ampere current rating, but the highest current rating is 41.6 and the input capacitance is 220 volt, sorry 220 microfarad, and this is 100 volt you can choose, and the output capacitance 200, standard is 200 or 250, okay, 250 volt, and the output capacitance is 2200, we have 2100 something. So, we have chosen the standard output capacitance that is available in market, that is 2200 microfarad, okay, and same 250 volt also. If it is not available, then you can go for this 450 volt capacitance also, and switching frequency again it is 10 kilohertz. So, we have to use the switching pulse of 10 kilohertz frequency. So, all these values will be used to do the simulation. So, going for here just I will show the simulation steps. So, which are now means already known to you. So, how to start create a model, then you have to create a new model following these steps. Okay. In the I think most of you are acquainted with Simulink, MATLAB Simulink. Those who does not know this, they can use this steps to make their new models. Okay. Then in the second stage you can add the blocks. The blocks are, we need battery, we need inductor, we need capacitors, all the components I will show in the next slide. Then you have to connect the blocks, okay. Then configure the parameters, like means you are dragging the suppose battery, the battery whatever will be available, suppose 12 volt, but as we need not connect to 12 volt batteries in series directly in simulation, you can put the battery parameter as 24 volt. Okay. Then you can run the model to run your means completely see your simulation. So, what are the specific blocks you need for doing this simulation? Here the sources means for this application we are going for this battery. Okay. You can get it from Simscape going to the electrical, then specialized power system, and inside the sources you will be getting this means this battery or fuel cell, all the sources, but here for this simulation we are using battery. Okay. And that too lead acid battery or lithium ion battery, that you can select from the going inside the battery. Okay. Which one you want to use? The switches you can choose MOSFET, IGBT. Okay. So, that is available also going through the power electronics components. Okay. Then all the filter components and the load, the resistor, inductor and capacitors are the loads that you will get inside the passive components, means Simscape, electrical and specialized power systems, under that the passive components you will be getting this. Okay. And these are this slide I will share, you can see all the components how to get it. Okay. And for the voltage and current measurement you will use the sensor measurement blocks, and for scopes you can use the inside the Simulink or commonly used blocks, you can get the scopes. Okay. So, you will drag all the components and you can put it in your newly framed the model MDL you have created. Okay. So, you will drag all the components, battery, then you will double click on each one of the component to fix the values to it. So, we are using suppose 42 Ah battery and voltage is 24 volt. Okay. And the switch is here, IGBT is used as a switch, the RLC components, the filter components, the inductor and the input capacitor, output capacitor components, and this is the voltage and current measurement unit which will show you the measured currents. Okay. And this is the display, the simulation means you can see the results through the scope, and this is here it will display the values. Okay. And to if you want to merge the data you means the signals you want to see, you can use the bus selector to see it. And this is the breaker to if here in this model we are using to switch on and switch it off to change the loads. Okay. So, this is after following those steps you can make your model which looks like this. Okay. Here the scope is connected which is showing the all battery parameters, SOC, the voltage and current of the battery. This is the current of the inductor current for which you are connected another scope here. Okay. And this is the switches you have used to connect and disconnect the loads, that is not actual switches. So, the BDC is formed using these two IGBTs. Okay. The bidirectional converter actually uses this is the one leg, but do not get confused, these are the switches to make the load on and off. If you are increasing the load or you are disconnecting the load by changing this pulses through the pulses you can have it. And here you can put another scope to see the your output voltage, the dislink voltage here. Okay. So, again the same thing. So, here this is the open loop system, you can say, means here there is no control system, means I have not put any control. You can put if you want to operate in a open loop mode, you can put the get pulses and then you put a inverter, give it to the lower leg. So, you can operate the bidirectional converter in open loop mode, but for the closed loop operation having the two dual means the two loops, that is the outer voltage loop and inner current loop. Okay. So, here the outer voltage loop, the voltage reference is fixed to 48 volt and the Kp Ki values we have already designed or tuned it. Okay. Here I have shown those parameters will be used for this doing this simulation. Sorry. Okay. Then you can after completing this means changing this PI values. Okay. You can run this. First you will set the battery voltage and you are fixing the load, and for the again the whole system is again you are doing for the with the load change condition also. Okay. This is the final output pulse which is given to turn on and turn off the both the switches of the bidirectional converter. So, you can run the simulation by pressing this run command. Okay. And you can see this is the final. So, this model I will share shortly and you can run it. In case of any problem we can see it in the tomorrow's class, because today I do not think now if you have any doubt we can discuss, but simulations you could take your time and run it, and after that tomorrow's lab demonstration you can discuss about the any problem in case of if you are facing any problem in doing the simulations. Okay. So, these are the results. So, here I have means this is done for the means the load power is varied. Here the load is from 600 volt to 800 volt, sorry 800 watt, 600 watt to 800 watt, then again it is changed to 500 watt. Okay. So, by switching on those here you are switching on, you are giving pulses to these switches to make the resistances means get connected to the circuit. Okay. So, you are varying the load in this way. So, first is the you are fixing the regulating the DC bus voltage. Okay. So, DC bus voltage is fixed at 48 volt. Okay. So, here there is a increase in load. So, there is a voltage dip. When there is a decrease in load, there is a voltage swell, means there is sudden increase in voltage, then it is again tracking the, and this tracking time is very fast. You can, the controller is tuned in such a way that it is very well regulating the bus voltage at 48 volt. Okay. And this is the DC bus voltage waveform, this is the corresponding load power waveform, and this is the inductor current waveform. Okay. Inductor current, you can say it is the battery current. Okay. So, here we have not connected any source, only the battery with the grid, means, so that is that so it is only operating in a discharging mode. So, discharging mode means, so battery current is always positive. Okay. You can see the when the load is increasing, the correspondingly the battery or the inductor current is increasing, and again when the load is decreasing, it is decreasing, but it is always supplying. And these are the waveforms of the battery, that is SOC. Battery SOC, initially we have fixed it to 80%. So, it is going on discharging. So, it clearly shows that it is operating in a discharging mode, or that is boost or buck, discharging boost mode of operation. And this is the battery voltage, and corresponding again here same thing is shown here, which is taken from this directly from this scope. Okay, for the battery parameters. Okay. So, this file I will share with you, and if you want to, you can change the parameters, the loads, the switching frequency to see the variation. If you change the inductance value, what is the effect. So, the with the model also you can do the analyze the results, what is affecting what, means the if you are varying the inductance, if you are increasing the switching frequency, or up to what value you can vary. So, those things you can see easily by running the simulations. Okay. So, this is the assignment question, where I have changed the input battery voltage to 36 volt. Okay. Output voltage is same fixed to 8, and the ripple switching frequency is changed to 20 kilohertz. You can try it to find out the steady state duty cycle of the bidirectional converter, and the inductance when it is operating. Obviously, we have done all the analysis for continuous conduction mode. So, calculate the inductance, the input capacitance, and the output capacitance values you can calculate. Okay. In the similar way, already I have given all the formulas, and the way how to do it also I told. Okay. So, this is about our thing, means what we have done, means the tutorial content for this today's class. But I will tell little bit about tomorrow's thing, which we are going to implement in the lab, means already it is implemented, it will be demonstrated to you in tomorrow's lab class. So, overall what was in our topic, our aim is to integrate the renewable energy system to the DC microgrid, and here in the course we have mainly focused on the mini hydro power plants. Okay. So, when you are going for this the renewable energy source, whether it is a mini hydro or wind. Okay. So, already you have seen the output is AC. Okay. And if you are taking the sources like PV or fuel cell, the output will be DC. So, based on that, step will be little different in the step. But here I have explained you the means I have tried to show you the design steps. So, first what you have to do, if you are going for a mini hydro or wind, it can be either way, means any energy source you are choosing. Okay. So, mini hydro design already you have learnt lot from such class. Okay. That was the main aim of this course. Okay. So, you have to choose the corresponding, after doing the power plant design, then coming for the electrical part, we have to choose the generator. Okay. So, generator, what can be the generator options also, that Professor Sarkar has already explained you, and for wind also there are synchronous generator or induction generators, you can go for it. Okay. Then you have to choose the suitable converter. So, here as the output for both these sources is AC. So, we have to go for AC to DC, and then depending on your bus voltage, those things, whether it will be buck or boost operation, that will be decided. Okay. And for both the cases you have to go for, means after this AC to DC conversion, okay, there can be single stage directly AC to DC doing the MPPT, as well as this can be in using a single converter AC to DC doing a MPPT operation, or you can have two stage, means AC to DC only rectification, then you can go for a DC to DC converter to do the MPP operation. So, how to do MPP, that is not the this course content. So, but after doing this part, you have to maintain the output voltage constant. So, that is the DC bus voltage regulation. Okay. So, that is the in the lower control lower level of control you are doing that. Then comes the in the upper level you are going for this power sharing and power management. Okay. So, these are the design steps when we are going to connect any RES to a microgrid. Okay. So, that its implementation you will see in tomorrow's class. So, here just I have tried to show the what we have implemented in our lab, but having two sources, two energy sources and two storages, but tomorrow we will see about having a single source and single storage, means battery energy storage and PV as the source. Okay. So, here we will be going for this DC to DC converter, this will be the storage DC to DC converter. Okay. And here for the supercapacitor again we are going for this DC to DC, this BDC. Okay. So, it is this topology is called here also this bidirectional converter what I have discussed just now. So, here we are going for this active topology, active configuration you can say. There are other configurations also, semi active, passive, but we are not discussing about those things. So, here first you have to design and develop the each source. First we have in our lab we have designed the wind energy conversion system, we have chosen the generator, then the corresponding AC to DC rectification we have done, then DC to DC converter we have used, this is a buck converter we have used for the MPP operation, which is interfaced again connected to DC bus. Okay. And this, so as this is a doing MPP operation, this bus voltage is fluctuating. Okay. So, to keep the bus voltage fixed at 48 volt, we have designed for a 48 volt system, then we are interfacing with this battery energy storage system, battery with the BDC. Okay. So, these things will be implemented, means already implemented, it will be explained to you tomorrow. So, then after developing this wind battery system, then we have integrated the supercapacitor to it, making it a hybrid storage, and after that we have also added a PV system to it, making it hybrid source. Okay. Combined source means PV and wind having complementary characteristics, and battery and supercapacitor having complementary characteristics. This is already implemented, but in this course you will be only seeing the first part. Okay. Means this part, PV with battery. Then, so in the low level of control we have tried to make the DC bus voltage constant. So, going to the upper level of control, higher level of control, where we are going for the power management, and the SOC estimation of the battery is also done. The overcharging, it is prevented from overcharging, discharging. Okay. For that we are the power management, the basic power equation is shown here for all type of sources. I have shown here 3 sources, but till now we have not added this one in our lab. Just as we have also done any source, number of sources you can, the total power, incoming power minus the losses occurring in the system should be equal to the load power plus or minus, means battery, when there is excess source power battery will store, or okay, and when there is a deficit power battery will supply. Okay, like that. This is the power management we have to implement. So, those things will be shown to you for a single system, and this is one photograph just I have shown for the PV as well as wind. So, here the ACIG based system is we have taken, okay. And PV, now this is for a very low power system we have designed initially, 200 watt within that operation, okay. And the corresponding converters and the sensor circuits, these are the converters, and the sensor circuits are also designed here, shown here. So, actually you can see in the lab tomorrow, okay. So, this is the content. So, these are the references, okay. If you have any question, you can ask. So, if you have no questions, so then I will go and I will share the model to you, the Simulink model, as well as I will give you the assignment question. So, you have to submit it by tomorrow before the valedictory. Any question? So, we can
Hello,
stop
ma'am.
here. Yes, tell me.
Yes, ma'am. What is if during the hardware implementation, the
Yeah.
control signals? What is the method followed for generating the control signals?
Method means platform you are talking about.
Yeah, platform. Yeah.
Means here we are showing means 2 will be showing tomorrow, means for this microgrid thing we will be showing dispatch based implementation, okay. And one DAB also we are going to show you the DAB demonstration. There this C2000 microcontroller will be implementing, okay. For microgrid we have used actually this dispatch, and also polarity based another wind based system we have developed, but tomorrow's class will be showing about the dispatch based implementation.
Okay, ma'am. Thank you.
Okay. So, we can close today's session. So, thank you all.